Hey guys. Okay, so believe it or not, we are almost done with exponential equations. This is our last topic. It's called growth and decay. So tomorrow, keep in mind that it's the Algebra 1 benchmark. You should be making plans to come up to the school, hopefully to take your benchmark. All students are required to take the benchmark exams. And then on Thursday, we're going to take a quiz. For Unit 9. So we won't take like a Unit 9 test because it's so short. It'll be like a 5-question quiz, and I'll put that in the grade book. So that's kind of the plan. And then from there, we're out of school on Friday. We'll move on, and we've got like your English 1-star test is coming up next week, and then we'll start reviewing. We're going to get into review mode. So that's kind of the plan for the rest of the year, pretty much. Okay, so we're going to start with some notes. And if you didn't grab the notes earlier in the week, here they are. This is what I'm working off of, the notes in this file. I'm going to bring them up over here. Might need the calculator, so let me bring that up too. Okay, so here we go. So we're going to talk about something called growth and decay that gets talked about a lot when you talk about exponentials. But really, those word problems that we were looking at on Friday, they're very similar to this. You're going to see the similarities, hopefully. Okay, so here's our equation. When we're talking about exponential growth and exponential decay, well, our equation is y equals a times b to the x, right? This is your exponent. So remember, that's what makes it exponential, is that the exponent is x. It's the variable. The variable is now the exponent. So your starting value is a. So whatever it starts with, that's your y-intercept. Same thing with lines. Your starting value is usually your y-intercept, and for us, that's the a value in this equation. And then your rate of growth or decay, now we're going to talk about growth, is the b value. That's what you put there. It's your rate of your growth. How fast is it growing? Okay, so let's look at a word problem. Now, this is what we did started looking at on Friday. So it says you have an account and you deposit $4,500 in that account. So there's your starting value. And it's paying you 5% interest compounded annually. So write an exponential function to model this scenario. Okay, so we're going to start with y equals, and then we need our starting value. That's a. That's the 4,500. And then we're going to multiply that times the rate and raise that to the power of x. So how much is it growing? That's what we have to decide. So here's what you need to remember. For growth, and I talked about this too on the problems on Friday. Think about it, you put money in an account and it's paying you interest. So this is like a savings account. This is not a loan. You deposit money into an account that pays interest. So the bank is giving you money, interest money, for putting money into a savings account. So if you multiply it by the 5%, remember you have to change that to a decimal, that's 0.05. That's not going to be enough. If you multiply 0.05 times 4,500, that's going to tell you what 5% of 4,500 is, but it's not going to tell you how much you have after 1 year, because after 1 year, you still have the $4,500 as long as you didn't draw it out, plus 5%. So I need the 0.05 plus 1. That's the total amount of money I'm going to have in my account. So when it's growth, you have to add 1. Now, if it's decay, you're going to subtract it from 1, right? We're seeing the similarities here. So this is growth because we're gaining money. Okay, so look at this table. It says write a rule. So they want to know, okay, here's my table. What's the rule? Now, you could use stat edit, put these values in stat edit. But we know it's exponential if we can look at our y values and see if they're changing by multiplying by some number. So I could think, well, how do I get from 1/8 to 1/2? How do I get from 1/2 to 2? How do I get from 2 to 8 and 8 to 32? So I could find the rule. Well, sometimes it's hard to see with fractions, but 2, how do I get from 2 to 8? I say 2 what? Well, times 4 will get me there. Is 8 times 4 32? Why, yes, it is. And then if we go back and we check 1/8 times 4, that is 1/2. And 1/2 times 4, because half of 4 is 2. So that right there, that's your rate. So we would need to write this rule, we just need our y-intercept. If we can find the y-intercept, the starting value, well, then we could write the function here. Well, remember, if you have a y-intercept, the x value is always 0. There's your y-intercept right there. So it's 2 times your rate is changing by 4 every time to the power of x. So what if we're even given a graph? This is growth. Do you see how this one is increasing? That's super important there to notice. If it's increasing, that's exponential growth. I'm going to erase that so we can see these points. So how do you write the rule if you've been given a graph? Well, we could look and find our y-intercept. Boom, it's right here. Looks like it's in between 4 and 6, so that would be 5. Now I just need to know how much it's changing by, and then I could figure out my entire function there. So I'm looking, here's a point. Now, luckily, this one has given us points. So I can see that to go from this point to this point up here, that's going from 5 to 10. That's times 5. And then here's the next point. So to go from this point to this point, to go from 10 to 20, oh my gosh, that's not times 5. I was like, what have I done, y'all? Did y'all see what I did there? To go from 5 to 10 is not times 5. It's times 2, Ms. Robinson. And to go from 10 to 20 is also times 2. So that's our rule right there. It's changing by 2. But again, you could find the coordinates for 2 points, and you could do stat edit in the calculator as well. So let's look at some examples if it is decay. Well, again, A is still your starting value. Our equation hasn't changed there. And B is still the rate, but now it's the rate of decay. Because when they're talking about decay, it means something that's decreasing. So growth, hello, increasing, that makes sense. Decay, decreasing. Okay, so let's look at a real world example. So you have a car that was purchased for $18,000. Now we know this, when we buy our car, a year later, our car is not worth what we paid for it. That's how cars work. Now, on the other hand, houses appreciate in value. They gain value. Somebody may have paid $30,000 for a house in 1950, and as long as you've lived in it and painted it when it needed painting and kept it up, it's going to be worth a lot more than $30,000 now. That's why people say houses are investments, but cars are not, because they get run down and they're not worth the value that you paid for them. So this car is depreciating. Again, that means decreasing in value by 20% each year. So write your function. Well, we know our starting value was the 18,000. So that's our y-intercept. Okay, so now we need to figure out the rate and raise it to a power of x. Well, they told us that the rate is depreciating by 20% each year. But again, because it's decay and exponential, you either have to add it to 1 or subtract it from 1. So because this one is decay, we're going to subtract. We're going to say 1 minus the 20% as a decimal. Well, that tells me that after 1 year, my car is only going to be worth 80% of its original value. That makes sense, right? That's what they told me. It loses 20% of its value. So there's our function right there. Okay, so if you're given a table, you can tell it's decay, because instead of multiplying, you should be dividing by something to get to a number. But remember, division is the same thing as multiplying by a fraction. So our rate is still going to be this fraction number. We want to use it as a fraction. We don't want to use it like, we can't say division, because we have to put a number in for our rate. Okay, so we can find our starting value again, remember, because your y-intercept is your starting value there. So it's 9. And we need to figure out our rate. What are we changing by each time? X is our exponent every time with an exponential. Well, to get from 81 to 27, I believe we're dividing by 3. But that's the same thing as multiplying by a third. To get from 27 to 9, yep, I can multiply by 1/3, or you're dividing by 3. So that's what's happening here. I'm multiplying by 1/3. So my rate is actually 1/3 for this one. But again, if you want, you can take that table and put it in stat edit, and it will give you the A and the B value. I'm just trying to illustrate to you a different way, because some of you like to see different ways to work problems. Okay, look at this graph. Do you see the difference in this one and the one above it? See how the one above it is increasing right to left? And this one is definitely decreasing. We're going down. It's like you're going down a slide. So this one is decay. Decay, the graph decreases. So if we're going to write a rule, we need our y-intercept, which is where? Boom, right here at 4. Then we need to know how much it's changing by, to the power of x. Okay, well, let's look at this then. So this one is changing. It's going from 4. My next point is 8. Well, actually, and then the next point here is 16. But remember how we said we're decreasing? So I really need to start up here at the top and go down the other direction. If you start going that direction, it's going to take you the wrong way because we're decreasing. So I'm going from 16 down to 8. How do you get from 16 to 8? Well, you have to divide by 2, right? Or it's multiplying by half. How do you get from 8 to 4? Oh, well, same thing. You're multiplying by a half. So this rate is 1/2. It's halving the value every time you go down. Okay, so the next assignment thing I want you to do is I want you to practice this. Here we go, growth and decay, penguin activity. Let me bring this up. I'm going to have to leave student view because I want to work one of these with you. So remember, click this link so you can get it to open a full-size tab. So here are these little penguin problems. So I'll just work the first slide with you. There's only like 6 slides. So the population of king penguins living on an island near New Zealand increased at a rate of 3.9% per year on average between 1930 and 2010 from a count of 3,400 penguins in 1930. Notice we're starting in 1930. So our initial value of penguins, so we started with what? 3,400 penguins. That's how many they started counting in 1930. So now we're going to determine whether this situation represents growth or decay. That's the thing. I want you to be able to look at these problems and go, oh, this was a decay or this is growth. So what did they tell us up here? They told us that it was increasing. Well, if it's increasing, that is definitely growth. So you're going to drag this little circle over your answer. Well, what's the rate that it's increasing at? Well, they told us it was 3.9%. So really, as a decimal, so you have to think about this, 3.9%, you would need to divide that by 100. And you're going to get, oh, wrong thing, that was an O, 0.039. Oh, I put too many decimals in there. It's supposed to be a 0, not a decimal. So that's our percent as a decimal. That's super important. You have to convert your percent to a decimal. So here's the equation. I'm giving you the equation, telling you you're going to have to either add it to your rate or to 1, or you're going to have to subtract it from 1. So formulate your equation. Well, we started with 3,400 penguins, and we know that our rate, we have to do 1 plus or minus our rate. Well, that's going to be plus because it's growth. So it's going to be 1 plus this rate, which is 1.039. And now this question here, we're going to apply it. If the trend continues, what will the population be in 2030 according to the model? So here is our model. The only place we can substitute in a number here is for x. So we need to figure out how long, what is the time, how long have we been increasing our penguin population here? So the population, they want to know in 2030. Well, when did we start counting our penguins? See, after 1930, we started counting them, and this is the initial value for 1930. So how many years have our penguins been populating here? 100 years. So we need to take this equation. I'm going to bring up my calculator here, and we're going to type in this part of the equation, but we're going to substitute in now our value for x because time is x. So we know it's been increasing for 100 years. So my starting value was 3,400. And I'm going to type it in just like this. I'm going to put my parentheses, and then I'm going to put my rate. And then I'm going to raise it to the power of 100 because that's my time. So this is how many penguins that we have. 155,967. Would we have 0.3 penguins? No. So that needs to make sense. So what we need to do is we need to round that to a whole number. So 155,967 penguins. Okay, so that's how you're going to go through and work. So the important thing to remember is that for each one of these, you're going to add it to one or you're going to subtract it from one to find your rate. Okay, so you have 5 more problems. Now, when you get done with this, make sure you come back over here and hit the submit button. You don't want to forget that. All right, guys, email me if you have any questions.